7.2 The Laws of Exponents. So the goal here is to discover rules for simplifying expressions involving powers. So let's recall what we see when we talk about a power. So a power is an expression made out of two parts, both the base and the exponent. So if you look at this power here, 5 and exponent 4, the base is 5 and the exponent is 4. Okay. Likewise, with this power here, the base is -5. It's what you see inside the brackets, and the exponent is 4. Over here, you can have a variable for your base. So the base is x, and the exponent is 3. Over here, you can have negative exponents as well. So the base is 7, and the exponent is -2. The next one, we have, be careful, if the exponent is the operates on the base it's attached to. So here the base is 5. That negative sign that you see acts out afterwards, after they evaluate this power. So it's negative and times 5 to the power of 4. Okay, so follow your order of operations, right? So the exponent here is 4. And here the base is going to be 3x, because this exponent 4 is acting, or it's operating on what you see inside the brackets. So inside the brackets I have 3x. So 3x is my base, and the exponent is 4. Okay, mathematically, a power is the repeated multiplication of the base and exponent, an exponent number of times. Okay, so the expanded form of 5 to the power of 4 is 5 times 5 times 5 times 5. And for -5 to the power of 4, it's -5 times -5 times -5 times -5. Okay. So how do you write a single value or variable as a power? If the exponent is not shown, the value is 1. So, for example, if you have x, you can write that in exponential form by saying x to the power of 1. Okay, so we don't normally write x to the power of 1. We just simplify that to just saying x. So anything with an exponent of 1 doesn't need to be written with the exponent of 1. Okay, discovering exponent laws. So expand and simplify each expression by writing as a single power. Compare the exponents in the expression with the exponent in the simplified expression and suggest a rule to satisfy the operation. Okay, so here's my first expression. 4 squared times 4 to the exponent 4. If I expand this, I would write this as 4 times 4. Okay, so that's 4 squared. And then I have times, and then 4 to the exponent 4 is just 4 times 4 times 4 times 4. Okay. Well, I can simplify everything that I see here by writing this as a base of 4. And well, how many do I have? I have 1, 2, 3, 4, 5, 6. So I can write 6. Is there a relationship between 2, 4 that you see in the question and the 6 when I simplify it? In fact, there is. If I add 2 and 4, I get 6. So when multiplying powers with the same base, add their exponents. So let's say generically or generally, if I have the base a raised to the exponent m times a to the exponent n, I can write this as a to the exponent m plus n. Add their exponents. Let's look at this one. 6 to the exponent 6. I can write that as 6 times 6 times 6 times 6 times 6 times 6. Divided by 6 to the exponent 3. So I can write that as 6 times 6 times 6. And because everything here is being multiplied on the top and on the bottom, I'm allowed to do some cancellations. So I can cancel a pair of 6's here, and a pair of 6's here, and a pair of 6's here, leaving me with 3 6's remaining. So 3 6's represents, or can be represented by 6 to the power of 3, because all of these are still being multiplied. The relationship between 6 and 3, your exponents in the question, and the 3 that when I simplify, well, if I subtract these exponents, 6 minus 3, I get 3. So when dividing powers with the same base, subtract the exponents. So a to the exponent m divided by a to the exponent n would be equal to a to the exponent m minus n. So this is just saying a is any general base. As long as you have the same base, you're dividing those two powers, you can subtract their exponents. Power to the power. So 3 squared. So 3 squared is 3. So 3 squared. Sorry about this. Sorry. 3 squared times 3 squared times 3 squared. Right? Because they're all raised to the power of 3. So it's going to have 3 squared, 3 squared, 3 squared. But what's 3 squared? 3 squared is just 3 times 3. So 3 times 3 times 3 times 3 times 3 times 3. So how many do I have here? I have 1, 2, 3, 4, 5, 6. So I can simplify that by saying 3 to the exponent 6. So is there a relationship here between 2, 3, and my simplified 6? There is. If I multiply 2 times 3, I'll get 6. So to simplify a power of a power, you multiply the exponents. So it's one power with one base, but raised to 2 exponents, you multiply those exponents. So a to the power of m times n. Okay. Next, we have a power of a product. Okay, so let's do this. 2xy times 2xy times 2xy. Good, because it's raised to exponent 3. But you can still multiply the 2's. So 2 times 2 times 2 is 8. I have 3 x's, so I have x cubed. And then I have 3 y's, y cubed. Okay, so I should write that here actually, 8x cubed, y cubed. So to simplify this power of a product, what could we do? Well, we can take the 3 and we can distribute it. Okay, and when we distribute it, 2 to the power of 3 is 8, and then x cubed and then y cubed. So you distribute the exponent to each part in the product. So each part in the product, if I have parts a and b, I would say a to the exponent m times b to the exponent m. Okay, you need to make sure that all the parts in that base are multiplied. Or it can be divided too, as we're going to see here. So the power of a quotient. So I have x over y times x over y times x over y times x over y, because we have it raised to the exponent 4. But I can simplify all of this by saying, well, I have here x to the power of 4, and on the bottom I have y to the power of 4. So to simplify a power of a quotient, you distribute the exponent to each part in the quotient. So if I have any generic base a over b, I can distribute the exponent m to each part on the top and the bottom. So I would have a to the power of m over b to the power of m. Let's do some examples. So when I say evaluate each, or the textbook says evaluate each, you want to actually evaluate what this is. So 9 squared is 9 times 9, which is 81. Okay. Negative 9 squared is negative 9 times negative 9. And remember, two negatives make a positive, so I will still have positive 81. Negative 9 without the brackets squared means I have a negative sign. And then 9 squared, which is 81, right? So 81, so negative 81. Okay, the negatives applied after you evaluate the exponent. Here I have 1 over 2 cubed, so that would be, again, distributing that 3 on the top and the bottom, 1 cubed over 2 cubed. But we don't say, well, 1 cubed is 1 times 1 times 1, we'll just say 1, and 2 cubed is 8, so 1 over 8. Okay. Negative 1/2 squared is negative 1/2 times negative 1/2, and that's equal to 1 over 4. Two negatives make a positive. And the 4 comes from 2 times 2, of course. Okay, example 2, simplify. So what does it mean to simplify instead of evaluate? Well, it means to write as a single power. We have 2 powers here, write as a single power. So here we have a division of 2 powers with the same base. So I'm going to subtract their exponents, and that's the quotient rule. Okay, so I'm going to rewrite the base, negative 3, 6 minus 4 is 2. So 6 minus 4, which is equal to 2. So negative 3 to the power of 2. Okay. If I ask you to evaluate, then you do one more step and you say negative 3 squared is equal to positive 9. But it just simplifies just keeping it as one single power. Part B, again, write the base. So the base is 7. Subtract the exponents. 8 minus 3 is 5. So 8 minus 3 equals 7 to the power of 5. Okay. Part C, I have power to a power. So I have to multiply the exponents. So I'm going to write the base 5, multiply the exponents 3 and 4, and that will give me 12. So 5 to the power of 12. Okay. So in questions like this, yeah, it would be hard to ask you to evaluate because you might need a calculator. So simplifying is good enough because evaluating this would result in a very big number. Okay, so you might have multiple rules put together. Okay, and you might have different bases too, but you might look at this and go, well, 3 and 9 are related. Well, 9 is just 3 times 3, so I could rewrite this whole thing. So 3 to the power of 15 times 3 to the power of 5 divided by, well, 9 is just 3 squared, right? So I can replace the 9 with the 3 squared, and don't forget the exponent 9 is still there, so I'll leave that there. Now, you might be wondering, which rule do I apply first? Well, when it comes to multiplication and division, the order doesn't particularly matter, but you might want to do the exponents first, the power of the power rule down here. Okay, so we'll take up the power on the power rule down here, and we'll also do the multiplication rule on top. So let's take care of that. So on the bottom, power of a power means that to multiply these exponents. So 2 times 9 is 18. So on the bottom, I have 3 to the power of 18. On the top, I have to add their exponents because of the multiplication rule. Two powers with the same base being multiplied means I have to add their exponents. So I'll write the base 3, add the exponents, 15 plus 5, I get 20. And now I'm left with a more simplified version, but I still have two powers with the same base being divided, so I have to subtract their exponents. So that's going to be 3 to the power of 20 minus 18. You only have to write the base once again, so then 3 to the power of 2. Okay. Okay, example number 3. Let's simplify this. So some more. X cubed to the power of 4. So we have the power of the power rule. You multiply those exponents. So x to the power of 12. Then you have your x squared. So x to the power of 12 times x squared. These are two powers being multiplied. Okay. And so add their exponents. So I have x to the power of 12 plus 2, which is 14. So x to the power of 14. Okay. Over here, again, power of the power rule generally should be first. Deal with those two powers. So here I'm going to write x cubed. Then I have x to the power of 4 times 2, which is 8. On the bottom, I have x to the power of 7. I can simplify the top. These two x's are being multiplied, so add their exponents. So 3 plus 8 is 11. So x to the power of 11 divided by x to the power of 7. Now the two powers are being divided, so I have to subtract their exponents. And we just check they are the same base, so we're good there. So rewrite the base x. 11 minus 7 is 4. Okay. Example 4, rewrite each with a common base or the base indicated. So rewrite 64 cubed as a power with a base of 4. Okay. So the question is, well, 4, how many times do I multiply 4 to get 64, right? So 4 times 4 is 16. If I multiply 4 again, I would get 64. So this is 64 can be written as, well, 4, and 4 is, is 3 times. So 4 cubed would give me 64, right? So 64 cubed is equal to 4. 64 can be written as 4 cubed. And don't forget, you still have the cubed there, so I'm going to write that there as well. So cubed to the power of 3 to the power of 3. And so if you have two multiplications here, if you have a power raised to a power, you can multiply the exponents. So I can simplify this to be 4 to the power of 3 times 3, which is 4 to the power of 9. And if you enter this result in your calculator, you'll get the same result as if you did 64 to the power of 3. Okay, so here I have two different powers. I need to write them as a common base, because you can't do anything unless you have a common base. So you can't go from 9 to 3, but you can go from 3 to 9. So 9 can be written as 3 squared. Don't forget you still have this 2, so that will go there. And you have your 3 squared here as well. Okay. Resolve, you gotta resolve this power of a power. So 3 squared squared is 3 to the power of 2 times 2, which is 4. And yeah, you also have your 3 squared over here. Now you have two powers with the same base, so you can write the base and then add their exponents. So 4 plus 2, which is 6. So 3 to the power of 6. And there you go. And that ends this video.